We usually picture volcanoes as towering, cone-shaped mountains launching fire into the sky. But that terrestrial view ignores a much more massive geological engine hiding beneath the surface of the world's oceans. In 2022, the Hunga Tonga Hunga Hapai eruption shattered our illusion of a quiet seafloor. The force of the blast tore through the water, creating a massive ash plume that expanded across the South Pacific. The shockwave generated a sonic boom heard thousands of miles away. It triggered massive tsunamis across multiple continents and severed the underwater cables that connected the region to the global internet. This destruction happens because of a specific collision, thousands of degrees of raw geological heat hitting billions of tons of highly pressurized, freezing seawater. We tend to view the vast ocean as a stabilizing buffer that absorbs impacts. However, the sheer weight of that water leaves us uniquely vulnerable, as it can turn a localized geological event into a global phenomenon. To see how this works, we have to look at the seafloor. Take the Manawai submarine volcano near New Zealand. When it erupts, the pressure violently ejects magma and can destabilize the surrounding seabed. When an underwater landslide collapses, the shift forces a colossal volume of ocean water upward into a vertical column. Gravity collapses that column, translating potential energy into a high-speed wave, accelerating away at hundreds of miles per hour. The 1883 eruption of Krakatoa demonstrated this lethal mechanism. While the volcano had a terrestrial peak, its underwater collapse generated waves that devastated coastal villages, leaving a lasting human cost on those living near the shore. While the heat and pressure of the magma blast start the process, the primary danger to land masses comes from the massive volume of water that blast sets in motion. Closer to the eruption site, the immediate underwater impact zone faces a different kind of destruction. Millions of tons of volcanic ash and debris rain down through the water, physically smothering nearby coral reefs. At the same time, the volcano releases carbon dioxide. The gas dissolves directly into the surrounding water, rapidly lowering the pH and altering local chemistry. This sudden ocean acidification is a localized catastrophe. The drop in pH dissolves the calcium carbonate shells of marine organisms, which can lead to a collapse of the local food chain. Yet these zones of ecological destruction also function as planetary nurseries. As waves of magma erupt into the freezing sea, they cool and solidify into rock. Eruption after eruption, this material stacks higher, breaching the surface. The 1960s Surtsey eruption and the 2021 Fukutoku Okanoba eruption both resulted in permanent new landmasses. This aerial view shows a freshly formed volcanic island, providing the foundation for an entirely new ecosystem. Underwater volcanoes operate on a cycle of extremes. The environment endures localized destruction to build the physical foundation for future life. While marine life deals with the lava, the rest of the planet feels what escapes the ocean and enters the upper atmosphere. Powerful submarine eruptions can punch through the ocean surface, ejecting aerosols and greenhouse gases high into the stratosphere, as captured in this historical photograph. Once these aerosols reach high altitudes, they scatter incoming sunlight. This leads to measurable temporary drops in global temperatures and degrades air quality for regions far downwind. But you don't have to look to the sky to see a volcano disrupt modern life. You can look back down to the deep sea, where humanity's critical digital infrastructure is at risk. Global telecommunications rely on undersea cables. Physical shock waves and trailing landslides from an eruption can sever these links, as seen during the Hunga Tonga event, which caused a near-total internet blackout for the nation. A submarine volcano is a planetary disruptor. It alters the Earth's climate from above and severs human connectivity from below. This nighttime view of an active eruption reminds us that the seafloor is a volatile, high-energy engine of creation and destruction. The specific consequences of an eruption rely on a complex mix of variables: the size of the blast, the depth of the vent, and the prevailing atmospheric conditions make predicting the exact impacts difficult. Because miles of seawater hide them from our direct line of sight, these submerged giants remain a significant, unmonitored geological blind spot. To protect coastal populations and secure our digital infrastructure, there is an urgent need to map the seafloor and actively monitor these submarine networks. By shifting our focus to these submerged networks, we can begin to anticipate the energy they release, preparing ourselves for the arrival of the next global ripple.